Hello everyone, my name is Lyle Regenvetter. I'm at the Decode lab at MIT, advised by Professor Fayez Ahmed, and today I'll be introducing the Design Target Achievement Index, a differentiable metric to enhance deep generative models in multi-objective inverse design. I'd like to start off the presentation with my personal view on why design automation is important. At its core, engineering design is usually iterative, it's time-consuming, costly, and often requires experience and engineering expertise. And as a society, this limits our design throughput. We of course have limited time, limited money, and only so many experienced designers. Designers are expensive, and this means that consumers are often paying a high premium for their products. Worse still, we don't have the resources to design products for marginal members in our society, since we only have the throughput to serve the common consumer. This often underserves impoverished communities and individuals with disabilities, exacerbating societal inequality. Finally, our limited design throughputs actually stagnates our technological progress by slowing down the rate that new technologies are adopted in consumer products. So with design automation, the overarching goal is to increase our design throughput. One way to do this is to lower the barrier of entry and democratize design. But not only do we want to make design more accessible, we want to make it more efficient and accelerate the design process for everyone. Furthermore, we want to discover higher performing designs and create cheaper and better products. So how exactly can we use design automation to scale and accelerate the design process, both for experienced and novice designers? Certainly there are many answers to this question, but I feel that one particular answer shows exceptional promise, and this is data-driven design. Now there are many types of data that are useful in design, but one that I'm personally interested in is using previous designs themselves as data. All of this engineering knowledge and intuition from millions of designers is baked into all of the products around us. And if we treat these products as data points, maybe we can develop design tools that understand this knowledge and intuition. And then perhaps these design tools will be able to assist us in our own design process or even generate entire designs on their own. Easier said than done, of course, but I hope you'll come to agree with me by the end of my presentation. My work today brings us a couple steps closer to this goal. Now, I'd like to note that data-driven design differs fundamentally from optimization-based design methods, which don't consider existing designs and solely focus on some specified optimization objective. This limits optimization-based approaches to engineering design principles that we, the designer, already know, since we have to specify these objectives. In contrast, data-driven design should be able to pick up on trends and patterns that we may not even be aware of. And for this reason, data-driven design tools have the capacity to learn much more complex design attributes than optimization-based approaches, at least on paper. But to do this, we need a method to extract incredibly complex knowledge from data in an autonomous fashion. One approach to do so, which has already revolutionized numerous fields, is deep learning. Deep learning propagates data through a series of kernel-based filters, matrix multiplications, and nonlinear activation functions, and has gained a reputation as a universal function approximator. And when used in the generative setting, deep learning has achieved some very impressive results. For quite a number of years now, deep generative models, or as I'll call them DGMs, have been able to generate artificial images of human faces that can pass as real. And recent results continue to be more and more impressive. For example, this image on the right was generated using a DGM when prompted for a rabbit detective sitting on a park bench and reading a newspaper in a Victorian setting. This illustration task would typically require time, talent, and experience, much like design, and the DGM executes this task very well. So on paper, these DGMs seem like an extremely promising approach for data-driven design synthesis. But it turns out that DGMs in engineering design come nowhere near the performance of DGMs in other fields like computer vision. For example, these airplane models were designed by a deep generative model. Now, whereas the last slide showed images that could have been photos or professional illustrations, fundamentally, we see something different here. These are 3D models of airplanes, and not particularly realistic ones at that. This is a promising start, but these are hardly the shiny, realistic designs that we would expect from powerful machine learning tools. Why not? Well, there's certainly many challenges with deep generative models in engineering design, such as the representation method and the dataset quality, some of which I've addressed in my previous work. But today, I'll be focusing on the following issues. DGMs have no notion of physical or geometric feasibility of designs and have no way to ensure that they will generate valid designs. In addition, DGMs typically neglect design quality or performance. And even recently introduced DGMs that do consider overall quality do not consider user-specified performance targets or design requirements. Let's go over these two ideas in a bit more detail. Okay, so the first issue is that DGMs have no concept of design feasibility. And this is a problem because depending on how you represent your designs, it may be very easy to generate infeasible ones. So why do DGMs struggle with this? Well, to understand this, we have to understand what deep generative models are trained to do. Given a data set with a particular data distribution, they generate sets of data points that mimic this distribution, something like you see here. You can think of this as a simple two-parameter design space with each point being one design. The problem is when you have relatively sparse data, as is very common in design datasets, you may not have a dense enough coverage of the design space to learn feasibility boundaries. So for example, perhaps only this blue region of the design space corresponds to products that are actually feasible. A well-trained generative model will have no chance of learning this complicated feasibility boundary based on this limited data. In contrast, if we have a data set of infeasible designs, in theory, we should be able to guide our DGM to better understand the feasibility boundary and actually observe it when synthesizing designs. I personally think that data sets of infeasible designs are actually a rather elegant approach to encouraging feasibility in generative models, and I'll explain later how we actually use this data in practice. For now, I'd like to touch on the other key issue with DGMs that I'll be discussing today. Deep generative models ignore performance targets. In general, we actually care about the performance of the products that we generate. Let's consider our simple two-parameter design space again. Perhaps these two parameters play a critical role in determining the safety factor of a design. And maybe we have a safety factor target of 5.5, meaning that only the green region of the design space satisfies this particular design target. Well, if we have performance values for the designs in our dataset, presumably we can sort our dataset into regions that satisfy the target and designs that don't satisfy the target. And we can then guide our DGM towards the region of the design space that satisfies this target. And if we simultaneously avoid infeasible regions, we should be able to ensure only feasible designs that meet design targets. But what happens when we have more than one performance objective and targets in these objectives that we can't simultaneously satisfy? Clearly, we need a bit more nuance than a simple yes or no sorting of our data with respect to performance targets. Now, in practice, we'd like to be able to assign a single aggregate score for a design's multi-objective performance, factoring in the multi-objective design targets. How do we design such a score? Well, to simplify the problem, we're going to assign a score for each of the performance objectives, then sum them into an aggregate score. But even assigning a single score for a given performance objective is difficult. First of all, we'd like a high score when we're exceeding targets, and a low score when we aren't. The further we're underperforming the target, the more we'd like our score to drop. But the further we outperform the target, the more we'd like our score to increase, but only to a certain extent, because if we're already way past our target, further improvements have less value. So if we express a score as a function of our performance to target ratio, we'd want something like this. Now, if we're taking a sum of scores over different objectives, we may want to prioritize certain objectives over others. In other words, we'd like a way to weight the contribution of each individual objective. As the designer, we can do this by selecting a parameter, which we call alpha, which adjusts the steepness of the scoring curve. We might also like to adjust the steepness that the curve falls off. This can be useful when we're dealing with objectives where further improvement over the target is more desirable than in other objectives. We can use another parameter, beta, to adjust this. And altogether, we can express this curve as a piecewise function, which we call the Design Target Achievement Index, or DTAI. We delve into the equations and mathematics in our paper, if interested. Okay, so we've talked about how to aggregate the target achievement performance of a design into a single score, considering multiple objectives. How do we use this in practice? Well, before we can compare a design to target values, we need performance values. And oftentimes, exact performance values require numerical simulation, like finite element analysis, which are too time-consuming and lack differentiability. So instead, we train a supervised predictive model to estimate design performance using a data set of design performance values. We use this predictor to estimate performance of generated designs, and we can then use our DTAI score to calculate an aggregate score for performance with respect to design targets. Next, we leverage the method we discussed earlier to encourage feasibility. We use a data set of infeasible designs to pre-train a classifier to predict the likelihood that a given design is feasible. We use this trained classifier to predict feasibility likelihoods for a batch of generated designs, and we then scale our DTAI scores by this feasibility likelihood for a feasibility weighted performance score. Now we could stop here and directly incorporate this score into our DGM training, but instead we borrow a technique from previous literature and incorporate a diversity kernel to encourage diversity of generated designs. I won't cover the details of this diversity scoring here, but this allows us to achieve a total diversity, feasibility, and performance score. Finally, we append the score to our DGM training score, and everything here is differentiable, so we propagate a learning signal back through the entire calculation to the DGM, which adjusts its generative procedure for the next cycle using gradient-based optimization. So in theory, we have a method that directly optimizes for performance, diversity, feasibility, and design targets. How does this perform on real engineering design problems? Well, training using infeasible designs isn't really a common approach, so there aren't many appropriate data sets for the problem. And as such, I've actually introduced a bicycle frame design data set in some of my previous work that includes infeasible designs and performance data over 10 structural performance values, such as weights and deflections and safety factors under different loading conditions. We benchmark our proposed framework against several baselines and deep generative models on this data set. We also propose a set of 8 evaluation metrics in our paper which consider overall performance, target achievement, feasibility, diversity, and novelty. If interested, I'd refer the listener to the paper for details. So from left to right, we test random sampling from the dataset, interpolation between dataset values, a generative adversarial network, and a conditional tabular GAN, which specializes in tabular data, as well as a multi-objective performance-aware diverse GAN, which established very convincing performance and diversity-aware airfoil design performance a couple years ago and makes for a very strong benchmark. Our proposed framework outperforms every competing deep generative model in every metric except diversity. And I'd like to especially highlight that we raise the average feasibility rate among baselines from under 73% to 95.9%, and the target success rate from under 34% to 69.8%. But not only are average scores higher, we can see that distributions of designs generated by our DGM consistently outperform distributions of designs generated by other methods. Shown here are a couple example metrics, the DTAI score itself, as well as the target success rate in both of which our methods demonstrate clearly superior performance over baselines. All right, some final thoughts to wrap up. Design automation can change our world, and data-driven design may be the way to do it. And while deep generative models have been extremely successful in other fields, several critical challenges have impeded their success in the design domain. As we discussed, 2 of these challenges are the difficulty of handling design feasibility and the inability to consider design performance targets. To address the former, I propose training feasibility classifiers using data sets of infeasible designs, and to address the latter, I propose an aggregate design target achievement index that seamlessly quantifies a design candidate's adherence to multi-objective performance targets. Finally, using these techniques, I propose a framework for deep generative model training that simultaneously optimizes for not only statistical similarity, but quality, target achievement, geometric feasibility, and diversity. I demonstrate that this framework outperforms previous high-performing generative models in almost every tested evaluation metric and outperforms baselines across the board. Thank you so much, and I'm looking forward to fielding any questions you may have.